We are jumping straight into the technical report for the new Kandinsky 5.0 foundation model family.
And this is not just an update, it's a total paradigm shift. We're looking at 3 new models: image Lite at 6 billion parameters, video Lite at 2 billion, and then the big one, the 19 billion parameter Video Pro.
The huge takeaway here, the thing you need to know, is the move away from traditional diffusion. Kandinsky 5.0 is the first in the family built on flow matching.
Exactly. It completely streamlines the latent trajectories, which is how they can use a unified architecture for both images and video. It simplifies the whole learning process.
And the engine behind that unification is their custom transformer, the Cross-DiT. That's a diffusion transformer with cross-attention built for, high-efficiency multimodal fusion.
And to handle the scale of video, they rolled out a pretty serious efficiency breakthrough called NABLA. That's a neighborhood adaptive block level attention.
Okay, that sounds complex.
It is, but the result is that it uses pooling to cut down computational complexity by a factor of, and this is wild, 4-day 96.
Wow. And that translates directly into speed, right? We're talking up to a 2.7x speed up for inference.
Yeah, whether you're making high-res images, say 124 pixels, or those longer 10-second video clips.
And the results really speak for themselves. In human evaluations against a big name like Sora, the lightweight Kandinsky 5.0 video Lite actually showed clear superiority in visual quality and motion dynamics.
But there is a trade-off. They do note that it sometimes lags a little in precise prompt following when you compare it to models like WAN 2.2. But that's your 1-minute summary.
Okay, let's unpack this evolution because the Kandinsky line has scaled, really aggressively.
Yeah.
It started back in late 2021 with Melovich, or Kandinsky 1.0. That was small, autoregressive, capped at 256 by 256.
Then the first big jump was Kandinsky 2.0. That was their move to diffusion models. They added multilingual support, and they doubled the resolution to 512.
And versions 3.0 and 4.0 were steady improvements, but 5.0 is where they really, rebuild the whole foundation.
Yeah, and that rebuild is all about the flow matching paradigm.
So for our listeners who are deep in diffusion models, why is flow matching such a fundamental leap?
It's all about simplicity, Traditional diffusion learns to predict the noise that was added over many, many steps. Flow matching, on the other hand, learns a continuous direct path from noise back to the data.
So it's a more efficient trajectory.
A much more efficient latent trajectory. And that allows them to train a single unified model for both images and video, which is a huge deal.
And this lets them split their focus into these specialized models.
Precisely. You get the Video Pro model, which is the 19 billion parameter powerhouse. It does text to video, image to video, pushing out 10-second clips at, really high resolutions. We're talking up to 14 under 8 pixels, like cinematic aspect ratios.
And on the other end, you have the Video Lite. Super efficient, just 2 billion parameters.
Yeah.
Still does 10-second clips, but caps out at 768 pixels. Great for, rapid work.
And then there's the dedicated image Lite model at 6 billion parameters, which is all about high-res T2R and some pretty sophisticated image editing. It's a very modular approach, all built on that same flow matching core.
Okay, let's get into the architecture.
Okay.
The engine is this Cross-DiT, and its input stream is fascinatingly complex. You've got text embeddings from Qwen 2.5, time embeddings, a single CLIP text embedding, and then visual latents from 2 different VAEs.
Right, from either the FLUX VAE or the Hunyuan Video VAE.
So why? Why combine all these different inputs? 2 text encoders, 2 VAEs.
It's all about robustness. It's a belt and suspenders approach. On the visual side, one VAE might be better at, say, high-fidelity reconstruction, while the other is optimized for video consistency.
Okay, so you get the best of both worlds.
Exactly. And on the text side, you get this really deep semantic understanding from the big Qwen encoder, but then you add the global, robust image-text alignment from that single CLIP embedding. It covers all your bases.
Which brings up a problem. The Qwen encoder is powerful, but it has a really limited context length, right? 256 tokens. How did they stop that from becoming a bottleneck?
They built a module for that, the Linguistic Token Refiner, or LTF. It's basically a cross-DT block that just skips the cross-attention part.
So its only job is to work on the text representation?
Its only job is to enhance the text representation. It's like they're pre-cleaning the text embeddings, getting rid of noise and positional bias before they even go into the main model.
That makes sense. The pre-trained encoder might have biases from its own training that you want to smooth out.
Exactly. The LTF refines the tokens, so the main Cross-DT block gets the absolute cleanest textual guidance possible.
So let's look at the Cross-DT block itself. It's sequential. Self-attention, then cross-attention, then the MLP. And they say this structure is a big advantage for video.
It is, and it comes down to efficiency in distributed training. By separating self-attention, which works on the visual tokens, from cross-attention, which brings in the text, the whole thing becomes much better at handling video clips of different lengths in the same batch.
Right, so you avoid all the slowdowns from concatenation or padding that you saw in older architectures.
You've got it. It just eliminates that structural bottleneck by design. So Cross-DiT solves the variable length problem, but then you have the next bottleneck for long high-res video, which is just sheer quadratic complexity.
And that leads us straight to the star of the show, NABLA. Neighborhood Adaptive Block Level Attention. This is the secret sauce for anything over 5 seconds or in HD.
It really is, and it's like a 3-step masterpiece of optimization. First, block-wise dimensionality reduction.
Okay, break that down.
Instead of calculating attention across every single token, they average pool the queries and keys into groups of 64. And since attention scales quadratically by n squared, this one move reduces the computation by a factor of 4096.
Wait, 4086 times? Just from pooling? That seems almost too simple. How do you not lose crucial details by just averaging things out like that?
That's where the adaptive part comes in. Step 2 is adaptive sparsification. They use cumulative distribution function thresholding to dynamically create content-aware sparse masks.
So it's not just dropping random blocks, it's intelligently figuring out which parts of the image or video matter most for the prompt.
Exactly. It focuses the attention mechanism only on the neighborhoods most likely to contain important information, filtering out all the noise or, big empty backgrounds.
So it's intelligently sparse. And what's the third piece?
The third piece is pure engineering. They use a token reordering trick called fractal flattening. It uses small spatial patches to make sure tokens that are next to each other in the image stay next to each other in memory.
Which optimizes memory access pattern.
Minimizes latency and gives you that final push to get up to a 2.7x speedup, all without really hurting the final quality.
That's an incredible stack of optimizations. Let's pivot to the data. We're talking a data set in the order of 10 petabytes streamed from S3. How do they manage data quality at that kind of scale?
Well, efficiency started with I/O. They pre-encoded everything into VAE latents and stored the latents, not the raw pixels. That alone cuts down bandwidth hugely and means no on-the-fly encoding.
And the filtering was extremely rigorous. I saw they use a dual model approach just for watermark detection.
Oh yeah, a classifier plus a YOLO detector, and that rigor was everywhere. They used quality models like TupiaQ and QAlign for aesthetics, a Scrat text detector to filter out videos with tons of burned-in subtitles.
But the thing that really jumped out at me was a complexity filtering. They weren't just filtering out bad images, they were filtering out boring ones.
Yes. That's so cool. They used SAM2 segmentation masks plus a Sobel filter, which finds edges, to just toss out images that were too simple, like plain backgrounds. It forces the training data to be rich in detail.
And on top of that, a synthetic annotation pipeline using huge multimodal models like Intern VL2 to generate high-quality English captions.
And a huge part of that data effort went into the specialized image-to-image data set for the image Lite model. They curated 150 million pairs.
And you can't just use CLIP similarity for that, right? Because you'd get a bunch of crops or minor reframings, not real edits.
Exactly. You'd get a picture of a house and then a zoomed-in shot of the same house. That doesn't teach the model how to change the house. So they used sophisticated geometric verification with LoftTR and Ransack
to make sure the image pairs were actual meaningful transformations.
Right. To ensure it really learned the difference between a baseball cap and a cowboy hat and could apply that change to the underlying structure. It's that rigor that lets them use their model soup strategy in the fine-tuning stage.
Okay, let's talk about that. Why souping? We know direct SFT can sometimes make a model forget how to be photorealistic.
Correct. It can cause stylistic regression. So what they did was they clustered all their data into 9 big domains: animals, people, tech, and so on. Then they fine-tuned a separate model on each little subdomain.
And they stopped training as soon as artifacts started to appear.
Right at that moment. Then, the final model isn't just a simple average of all those checkpoints. It's a weighted average, with the weights proportional to the square root of the subdomain's size.
So the bigger, more robust, fine-tuned models have more influence, but you still get the benefit from the niche ones.
And that's how they restored the photorealism and compositional quality. It's a really clever approach.
Moving to infrastructure, I was really impressed by the data loader design and the dynamic batching.
It's so smart. They stream from S3 into different RAM queues based on aspect ratio 1 for 1.1, 1 for 16.9, etc. Then the main process just pulls from those queues to build a batch.
So it's packing in a bunch of shorter videos together to fill up the batch,
Yeah.
making sure there's no wasted GPU time that you'd get if every video had to be the same length.
It's all about maximizing GPU utilization. And to maximize memory, especially for that 19B monster, they did something I've never seen before. Activation checkpointing with host offloading.
This sounds like a huge win.
It is. So instead of keeping all the activations on the GPU for the backward pass, which is a massive memory hog, they asynchronously move the inputs of each transformer block off to the host CPU RAM.
It's like giving the GPU its own dedicated high-speed swap drive just for activations.
That's a great way to put it. And it gives them this huge reduction in peak activation memory without any noticeable slowdown. It's what let them train the Video Pro model at all.
And one last polish for the image model. RL-based post-training with the DRAFTK method. What was the trick with their reward model?
The fascinating part is they skipped human annotators. They trained their reward model, which was a Clune model, on a simple relative heuristic. A pre-trained image is worse than an SFT image, which is worse than a real image.
And the actual RL goal was to make the generated image better than a real image from the training set.
Yeah, better than an image from the SFT dataset. By focusing on that relative difference, the reward model becomes way more robust than if you try to give every image some absolute quality score.
Okay, let's talk results. The human evils pitting the small Kandinsky video Lite against Sora were pretty striking.
They really were, especially given the size difference. K5.0 Lite was preferred for visual quality 70% of the time, and for motion dynamics 67% of the time. It also had fewer artifacts.
But there's that trade-off again.
The trade-off. The weakness is still prompt adherence. Key 5.0 was only preferred 53% of the time against Sora, and it did lag behind other models there.
So it's that classic tension, incredible visual realism, but at the cost of some semantic precision on really complex prompts.
Which they know. It's what they're working on next.
And we have to mention the efficiency from the distillation, the flash variant.
Oh yeah, those are huge. They use only 16 steps, or NFEs, compared to 100 for the standard model.
The time savings must be enormous.
Take the Video Pro model making a 10-second clip on an H100. The standard version takes almost 20 minutes. The flash version cuts that down to just about 4 minutes.
That's the difference between a research toy and a commercial tool.
Absolutely. And the use cases are broad. From photorealistic images with legible text all the way to high-res video for marketing and creative work.
So to wrap this up, Kandinsky 5.0 is a state-of-the-art suite, and it's all driven by that architectural shift to flow matching, plus these incredible optimizations like CrossDiT, NABLA, and host offloading.
And despite all these wins, they're pretty clear about the limitations. They need better text-visual alignment, which means finding text encoders with longer context windows. And they need better temporal consistency for really complex physics beyond 10 seconds.
They also bring up the ongoing challenge of sociocultural bias in the training data, which is something the entire field is wrestling with.
And their stated long-term goal is really ambitious, to take all these specialized models and merge them into a single unified foundational visual model.
And achieving that, especially if you want to move it beyond the data center, raises a really interesting question. And this is for you, the listener, to think about. Given the amazing memory and speed optimizations they've already built, what do you think are the next architectural or data handling breakthroughs needed to get to true, real-time 24+ frames per second, high-res multimedia generation on consumer-grade hardware?